Let's do one more example of ODEs with Dirac delta, this time with non-zero initial conditions. So let's try to solve y double prime plus 3y prime plus 2y is Dirac at 3 with initial position 2 and initial velocity minus 3. And if you want, this is like a mass spring equation with damping, but where you have a little kick at 3. And of course, just as usual, the first step is to take the L. So take Laplace transforms. So take the L. So Laplace transform of y double prime plus 3 Laplace transform of y prime plus 2 Laplace transform of y is Laplace transform of Dirac at 3. So delta t minus 3. Now I realize it's like a Pokemon game, but where suddenly you see this new Pokemon because Dirac delta. But we're not scared because we're Pokemon masters. Okay, and now let's use the miracle. So L of y double prime is s squared L of y minus s y of 0 minus y prime of 0 and then plus 3. Let's see. SL of y minus y of 0 and then here plus 2 L of y. Again, what is Laplace of Dirac at 3? It becomes exponential. So E of minus 3s. We covered that in a previous video. And usually we're happy and we can just ignore the initial conditions, but here we can't. So this becomes s squared L of y, and then y of 0 is 2, so minus 2s. Careful, y prime of 0 is minus 3, so minus that becomes plus 3. I know, pesky algebra mistakes. And then 3s L of y minus 3 times y of 0, so minus 3 times 2, so minus 6. And then plus 2 L of y equals E of minus 3s. And then you gather the L of y's. So you get s squared plus 3s minus 2. So s squared plus 3s. Sorry, did I say minus 2? I meant to say plus 2. Which again is the auxiliary equation times L of y. And don't forget about the other term. So minus 2s and then minus 3 equals E of minus 3s. And so we get s squared plus 3s plus 2L of y equals 2s plus 3 plus E of minus 3s. And then you want to divide by the auxiliary equation. And just be a little bit careful. So we have two terms here. So on the one hand, we have L of y is 2s plus 3 over s squared plus 3s plus 2. And then plus, if you want, 1 over s squared plus 3s plus 2. Then times E of minus 3s. And be careful, so students are sometimes confused about that e of minus 3s just goes with that second term. And then you may wonder, what time is it? It's partial fractions time. I mean, technically, it's 11:09 a.m., the recording of this video, but it's kind of irrelevant. So partial fractions. And yes, here I was especially evil because turns out you have to do two partial fractions. Because there's this first term, and then you'll see the second term. They're not too bad. So for the first term, well, we have 2s plus 3. This s squared plus 3s plus 3, that's s plus 1 times s plus 2. So you split it up as a times s plus 1 plus b times s plus 2. And then you can see the details in the notes, but turns out you get a equals 1 and b equals 1. So it's just 1 over s plus 1 plus 1 over s plus 2. Again, put everything on a common denominator, compare all the coefficients, and you end up getting a equals 1 and b equals 1. And for the second term, same thing. Second term. So we have 1 over s plus 1 times s plus 2. Again, you split it up as a over s plus 1 plus b over s plus 2. And you end up getting a equals 1 and b equals minus 1. B equals minus 1. And turns out here's the difference. 1 over s plus 1 minus 1 over s plus 2. So once again, two partial fractions, but hopefully not too bad. And then we want to go back. So what we had so far, L of y, was 2s plus 3 2s plus 3 over s squared plus 3s plus 2, and then plus this, let me see, put that here, b equals minus 1. 1 over s squared plus 3s plus 2 times e of minus 3s. Then what did we do? We partially fractated those. So this is 1 over s plus 1 plus 1 over s plus 2. And then plus 1 over s plus 1 minus 1 over s plus 2. And then e of minus 3s. And again, hopefully now you actually see why partial fractions is so nice. Because it's so much easier to write this as a sum and a difference instead of those nasty fractions. All right, and once again, let's try to recognize this as Laplace transforms. So I think it's e of minus t plus e of minus 2t. Minus because we have s plus 1 and not s minus 1. And then plus L of e of minus t minus e of minus 2t. And an exponential term, e of minus 3s. And remember, what does this e of minus 3s do? It shifts and jumps. So what you end up getting is, if you want L, we still have L of e minus t plus e minus 2t, and then plus e of minus, I think, t minus 3. And then minus e of minus 2, t minus 3. and then Dirac, no, not Dirac, Heaviside at 3. So U3 of t. You jump at 3. And I know it's t minus 3 because we're shifting by 3 here. Signs seem a bit awkward, but yeah. Okay, very good. And that is now our solution. So now you feel happy because we find that our solution is e minus t plus e minus 2t, and then plus e minus t minus 3 minus e of minus 2 t minus 3 times a jump u3 of t. And once again, let's see what this looks like. So satisfying when the box becomes a box and not a circle. So once again, what was the application of this? So think masses and springs or an electric circuit where something happens at 3. And precisely what happens is, before that, we have an exponential term. Right? It basically becomes e of minus t times e of minus 2t. Maybe like this. And then suddenly at t equals 3, you get a little kick. And it turns out it becomes like that in the end. Again, which is really cool because once again, you see the solution coming to life or the solution being perturbed at t equals 3. And we're able to do that using the magic of Dirac delta.